video is for the average finite differences. So we are going to be writing linear functions from average finite differences. And this is more typical with your real world data. Real world data is not nice and neat like mathematically created data. So we're going to look at the radius of a tree, and we're going to look at average acceleration. Sorry, guys. All right, Marion measured the width of tree rings from a core sample she took from a post oak tree. From the tree ring width, she calculated the radius of the tree and displayed her results in the table below. Use the information from the table to write a function rule. All right, so change in x every time. We're adding 1. Every time, adding 1. So that's our change in x. Our change in y, we're going to calculate just like we've done with the other finite differences. Work backwards, 3.1 minus 2.5. So here we added 0.6. Here we added 0.4. 0.4 plus 0.5. Again, if you cannot do them in your head, that is okay. Use your calculator just for time on the notes. So those are my changes in y. So we're going to calculate the finite differences. So that's what we did. We calculated the finite differences. Then we're going to look at, are the first differences in the radius constant? So this is not the same value every time. So no, but they are close. Now that's important, because if they're not close, these are within a tenth, 2/10 with an accuracy. If they're not close, or say you've got a bunch of sign changes, that indicates that, hey, maybe this is not a linear function, maybe it's a quadratic function. All right, we're going to find the average finite difference. To find averages, add all your values up. So 0.6 plus 0.4 plus 0.4, that's just these numbers down here. And then you're going to divide by the number of pieces of data. 1, 2, 3, 4, 5, 6. All right, if we divide that out, and again, in your calculator, you can just make a fraction. Divided by 6. That is my average finite difference. We're going to use that average finite difference in radius and the information from the table to write a function rule. So y equals, this is going to be our slope. Your average finite difference is going to be your slope. Y-intercept, they give it to me. X0, y is 2.5. Now, what does the slope from your function rule mean in the context of this situation? So in this real world data, what does that 0.5 represent? So 0.5 represents the number of centimeters. The reason I know that it's centimeters, radius is centimeter. That the radius of the tree grows each year. What does the y-intercept from your function rule mean in the context of this situation? This number right here. Write this small because we need to put something down here. It did not print. 2.5 represents the radius of the tree when the data was first collected. So the slope is the change over time, how much it changes each year. Your y-intercept is your starting point. Now, what should be down here on the bottom? It's bottom here. Number 7, okay, should say, use your model to predict the radius of the tree after 15 years. So you can just write 15 years. Now, years is an X. So what we can do is we can plug that 15 into our equation that we wrote. The other thing that we can do is in our calculator, we can go to graph and we can type our equation in. We can pull up the table and we can go to where X is 15. So that radius would be 10 centimeters. All right, number 8 should have said, use your model to predict when the radius will equal 12.5 centimeters. Radius is a y, so same thing. We could plug this radius in for y. And that's honestly what I would do. I would solve that equation because there's no guarantee, and I think this one does, there's no guarantee that data point is going to be on the table. So to remember to solve that, solve the equation like you normally would, or menu 3.1, 12.5 equals 0.5x plus 2.5 comma x. So 2 different ways to do it, and you can use the table. Always check that first. That's going to be your easiest method. So this would be, let's see, equals 20 years. All right, so now we're going to look at average acceleration. So scientists are conducting an experiment, typo, to see how long it would take a car to coast to a stop if the brakes were inoperable. The first few seconds of data are recorded in the table below. So we're going to calculate the finite differences. So here we're adding 1 every time. Here we're subtracting 3. Here we're subtracting 4. Here we're subtracting 2. Here we're subtracting 3. So average first finite difference. All right. I'm going to make a fraction. And I'm going to add all of my finite differences. -3 plus -4 plus -2 plus -3. I'm going to divide that by 4. So that is -3. All right, we're going to use the average acceleration and first finite differences in the x values to determine the y-intercept. So here, we know we're adding 1. The change here, I'm going to use this. The change here is about -3 every time. So we can use that same ideology. B minus 3 should equal 65, or 65 minus b, because again, when we're finding finite differences, we work backwards. So we would do 65 minus 65, start over. 62 minus 65 gives me -3. So 65 minus b should also give me a -3. So we can solve that. And b would equal 68. So use that average finite difference to find your y-intercept. All right, write a linear function model for this situation. So your average finite difference is your slope. This was the y-intercept that we found. Use the linear function model to predict when the car will come to a complete stop. All right, when the car comes to a complete stop, the speed is going to be 0. So I want to know when the y value is going to be 0. So I'm going to plug a 0 in for the y. And if I solve that, I get kind of a weird number there, but I'm going to approximate here. So we're going to say, we're going to round this. X is approximately, if we round that up, 23 seconds. Okay, that is the most accurate answer. This would be 22 2/3. I can change that to a fraction. I can approximate it to a fraction. So 68, if you wanted to be accurate, X equals 68 over 3 seconds. Most of the time I will tell you whether you need a round or not.